So with that, I'm going to introduce our first plenary speaker, who's going to help set that stage. Our first speaker is Kelly Redmond. Dr. Kelly Redmond is the Deputy Director and Regional Climatologist with the Western Regional Climate Center at the Desert Research Institute. He has a BS degree in physics from MIT. He also has an MS and PhD in meteorology from the University of Wisconsin in Madison. Dr. Redmond, he works on a lot of different projects, and I can tell you he travels a lot too, and he'll tell you that too, because he talks a lot about this to a lot of different audiences. But some of the different projects that he works on are the National Integrated Drought Information System, the NOAA Regional Integrated Science and Assessment, the Department of Interior Climate Science Center Program Council. And then, as I said, he interacts a lot with all different types of groups, whether it's public, print, radio, and television media across the West, the focus being on the West. He's also, in his profession, he's active in the American Meteorological Society. In 2008, he received the Applied Climatology Award from the AMS, and he was also elected a fellow of the AMS. So with that, please join me in welcoming Dr. Kelly Redmond.
Okay, thanks a lot, Tom. So, coming here in several capacities, mostly with the Regional Climate Center program, but also the RESA program, California Nevada Applications Program, and part of the Southwest Climate Science Center as well. And I have a few slides in here that a little bit detailed, and in the interest of time, I might skip through them, but I wanted them there so that you can look at them later when they put this up on the web. So, a few things I might go through kind of fast. Just an overall comment, this really is a problem. It begins in physics and it ends up in the lap of society. So what the heck is all the fuss about? For any of you who are about 50 years old or so, when you were born, since then, the amount of carbon dioxide in the air has gone up about 25%. And so actually, if you're not off during this talk, you're excused for that reason. It's currently about 395 parts per million, and it's still on the way up. So as you were walking in here this morning, you probably noticed all these big arrows up in the sky. And just like you and I have a checking account, the atmosphere has an energy account, and it has energy coming in from the sun, which is more or less balanced by the energy that's emitted by the system as infrared radiation. It runs around 235 watts per meter squared. So a watt is a joule per second per meter squared. And the effect of, in a nutshell, the effect of the greenhouse gases is to, if I can make the cursor work here, is to take this number and reduce it a little bit by a few watts per meter squared, but we still have the same amount coming in. So we have the same amount coming in, we have less going out, energy starts to accumulate in the system starts to heat up as a consequence, and as it heats up, it starts to boost the amount going out, and it comes back into balance, except it doesn't have a chance to come back into balance because we keep increasing the greenhouse gases. So that kind of in a nutshell is what this greenhouse problem is all about. How much energy are we talking about here? Well, think about an ordinary 60-watt light bulb, and they should actually be called heat bulbs because that's mostly what they give off. And if you think about doubling the carbon dioxide content in the atmosphere, that would add about 4 watts per meter squared. Well, for a 60-watt light bulb, we take the area of this stage right here. It's roughly maybe 4 by 4 meters times 4 watts per meter squared. It's about 60 watts. So how big is the Earth? Well, I think everybody knows it's 510 million square kilometers. So, how many light bulbs like that would it take to cover the Earth? You work it out, it's about 30 trillion, okay? So if we take the whole Earth and cover it with these light bulbs, this is about like what the greenhouse problem is when we double it. As of 2013, we've put out about 19 trillion of these light bulbs, and I saw some people yesterday busy putting out some more. So we have influences that warm the climate and influences that cool the climate. Greenhouse gases are the primary one. Of the greenhouse gases, carbon dioxide is about 2/3 of the issue. Also methane, nitrous oxide, ozone, and chlorofluorocarbons are important as well. A little bit of warming from some kinds of soot, from land use changes, and from solar activity, which is pretty minor. And this is compensated somewhat by the cooling influences, which come from pollution and most aerosols in the form of direct reflection, and also in terms of changing the properties of cloud droplets, making clouds brighter. There's the occasional odd volcano, and there's some land use changes. It's worth noting at this point that carbon dioxide has 2 or 3 consequences. First of all, it has an effect on the physical side of climate. Secondly, plants love carbon dioxide, so it has an effect on the biology of the planet. The third thing, a fair amount of the carbon dioxide going into the atmosphere is going into the ocean, it's going into solution, it's making the oceans more acidic. This is not really a climate issue per se, because it's not very tied to climate. But it's rather than a climate issue, it's a chemistry issue. But it's a major issue all by itself, and I would deem it almost as important, or maybe even more, changing the chemistry of the ocean to changing the climate. And it's a good reason to remove carbon dioxide all by itself, even if there was no climate change. Just a little side comment on that. So here's an example of some of the pollution you see. This is over Eastern Asia. The very fact that it looks white means that energy is being reflected back from the Earth to space. It's not participating in the system. And here's an example of a volcano up in this redoubt up near Homer in Alaska. And so we can form a history back to 1880 of the major influences on climate. The warming influences on the top and the cooling influences on the bottom. And the major one on the warming side is greenhouse gases, which are on their way up, and they're probably going to keep going up. We have the 2 blue curves, the purple curves right here, which are the direct and indirect effects of aerosols. We have the odd volcanoes, these downward spikes here. Volcanoes cool the planet. The tiny little wiggle you see right here in brown, that's solar variation. It's about 1 watt per meter squared, about 0.1%. So we can put these in a climate model, and we just run these models, and I won't say a lot about how these models work, and we go to Madam Olga and have her generate a bunch of stochastic scenarios out into the future. And a couple of ways of presenting some of these. These go back a ways, but they really haven't changed all that much in the last 5 or 10 years in the Great Basin. So here's one example that Mike Dettinger has helped put together for the western side of the Great Basin. You run these models starting in your 1900, or 1800, 1900, and you run them forward a couple hundred years, and with and without all these greenhouse gases. And when you subtract one from the other, and run a bunch of times, so there's a bunch of examples here, starting around maybe 1975 or so, they start to depart from the case where there wasn't the greenhouse gases, and here we are in the year 2013, and so we should have come up maybe about a degree C or so, and we're going up to a bright and glorious future, as you can see. How about precipitation? Precipitation, a little bit different story. In the net, most of these models are kind of hovering around zero, in zero change in the annual precipitation. Let's go a little further east in the Great Basin, take another view. And I'd like to thank John Abatsoglu, who's a former postdoc of mine. He's up at the University of Idaho now. Very nice diagram here. So we have a bunch of climate models, and we're looking at the early, middle, and late 21st century. And like you go to a doctor, we're going to the climate doctor here, and instead of getting a second opinion, we're getting 15 second opinions about what the climate might do. And this is about the temperature. And the black dots are the mean annual temperature, shown here. And all the individual models, what they're saying at that location about temperature, are shown as the plus signs there. So there's the range of opinions, basically, coming from these different models. And we can divide it into winter, spring, summer, fall, which is the colored dots here. Find them. There's winter in blue, winter, spring, summer, fall, winter, spring, summer, fall, winter, spring, summer, fall, going out in the future. Not a lot of seasonal variation that is shown here. And none of these models are predicting anything in the realm of cooling. It's all how much warming. This is the old CMIP 3 models, by the way. The newer models, which are called CMIP 5, are pretty much saying more or less the same thing. When we look at precipitation over there, here's the annual total right here in this little open circle. Middle century and late century, it really isn't changing very much according to these models. They're plus and minus from that. But you do see another feature here. It's not just how much you get on an annual basis, how it's distributed within the year. So the winter, which is the blue, starts to get a little bit warmer, and the spring and the summer in the green and red start to get a little bit drier. So the effect of this is sort of the precipitation season is mushed a little bit more into the winter, and it's reduced in the spring and the summer. There's been another set of models under a project called NARCAP, where they run a bunch of regional models for the United States. And this is a little bit further into the future. It's comparing the period around 2055 minus the last 30 years or so. And this shows the spatial distribution. On top is the annual, and then there's winter, spring, summer, and fall. And they all warm up. They warm up a little bit more in the summer, also in the fall, maybe a little bit less in the winter. But you can see the spatial pattern there, a little bit more in the interior, right along the coast, because of the presence of the ocean, might take a little bit longer to warm up. If we look at the precipitation now and look at global climate models, this was put together a few years ago, but it hasn't changed appreciably. This is the average of 19 climate models, and it's for a period around 2030, plus or minus 10 years, so that's only 17 years from now. And what they're indicating is that up along the Canadian border, the areas in blue will get a little bit wetter, a few percent wetter, 2, 3, 4, 5% wetter. Along the southern border, 2, 3, 4, 5% drier. And you can see a sort of dividing line here. It runs through about the middle of the west. Sort of, I always use I-80 as kind of the dividing line. The eastbound lane is going to get drier, the westbound lane is going to get wetter. And this is the NARCAP results. This puts a little bit more spatial resolution to these. It's broadly similar in the same picture. Has maybe the drying line shifted a little bit further north. Winter, generally wetter over much of the United States, but then spring and especially summer, border to border drier, and in the fall, a little bit more in the southwest, drier in those 3 seasons. So what's it been doing? So this is the for these 11 western states here, this is basically the area covered by my job, plus Alaska and Hawaii. This is the history of the temperature based on the surface stations, the co-op stations, since 1895 for the 11 western states, and several kinds of behavior here. You see lots of up and down from one year to the next, as we sort of typically expect with climate. You see broader patterns that last a few years. That's indicated by a running mean in the blue line, that are variations on the scale of decades or so, 1 or 2 decades. And then starting about 1976, which is a coincidence with that last picture I showed from Mike Dettinger, there's been a sort of an unsteady warming taking place, which climbed up to the late 90s and then sort of leveled off. Then we've just gone through 4 relatively cool years. They're cool relative to the recent past, but they're still warmer than the long-term average. We've gone through 4 cool years, and then last year really shot up again, the value over here on the right-hand side, and it almost equaled the all-time warm year in the West, which is 1934. So you might remember some of these characteristics here for a little bit later. And this sort of lines up. This is not a easy to read graph, but the top line is the global mean temperature up to 2012. And these 2 graphs have a fair amount of similarity to them. They start on the cool side and end up on the warm side. They also flatten out. So there's a fair mimicking of the global signal in the western states. So we have a little thing on the web called the Nevada Climate Tracker, and John Abotsoglu helps update this every month. And when you go in and look at this, what's the state of Nevada been doing? This is based on the PRISM data. So this is 4-kilometer data averaged over all the pixels in the state of Nevada, calendar year average, from 1895 up through 2012. And it started on the cool side, There's a long period here where it didn't do too much, and then starting about the mid-90s or so, it's warmed up quite a bit, and last year was second or third warmest in this record, 1934 in there too. If we look a little further and look at the daytime maximums, this is the history of the daytime maximums in Nevada, they also started cool, but then we've had actually quite a long period here, you might even say it goes right through present, where we haven't had a lot of warming taking place in the state of Nevada in the daytime. Contrast this with what's taking place at night when we're all asleep, and that has a kind of an unsteady warming in the first 2/3 of this record, but it's really popped up since about 1990, 1995 or so, and last year had the highest minimums in the record. And this is also true of the Colorado River Basin and so forth. So what's happened in the United States during the last 10 years or so is just a series of maps of the departure from long-term climatology for the years 2000 up through present. And for quite a while there, it was seeming like the West was really getting picked on. It was above normal, above normal, above normal, above normal, above normal, above. Now the rest of the country starts to get in on the act. Starting around 2008, 2009, we've had decidedly large areas of cool temperatures in the Midwest and parts of the West. Same thing in 2009. We continue this on. 2010, a little bit less warm. 2011, again kind of cool, and then 2012 was the warmest year in the United States by some margin. We only have 2 months in for this year, and it started out decidedly cool in the western states, January and February. How about precipitation? The state of Nevada. This is a water year precipitation. I guess one thing that you can see by looking at this, there's no decided trends. If there's going to be a trend, when you have a record as noisy as precipitation, it goes up and down so much, it's going to be a while before you're going to be able to decisively say that it is getting wetter or drier. We had the maximum in Nevada is right around the late 70s, early 80s, and then it's come down a little bit since then. John Abatsaglu and I just wrote a chapter for a book on North American climate change, and I've got some graphs out here. I don't want to really dwell on these because they're a little too small for showing a lot, but the gist of these is that we have the annual on the left, and we have the seasons on the right, and we have the period from 1900, the last 110 years on the top, the last 60 years in the middle, and the last 35 years. The idea is just to see, is anything changing, is it accelerating? And you see bolder colors on the lower graph there, the lower line, which is indicating that the trends are becoming more accentuated in the last 25 or 35 years or so. So in the West, we have these big cities, and this is Reno, taken from Southwest Airlines. And this is, we have these masses of people living here who depend on the masses of snow up in the mountains here. This is their water supply. 7.5 inches is not enough to support a population. Most western cities live off nearby mountains, and we have a range here going from about 7 inches up to about 55 to 70 in the mountains nearby. So we've invented a little tool called the freezing level tracker, because the freezing level is so important in the western states. What's the freezing level done? This is over near Elko, and this is updated every day. And you can go in and do this yourself. And this goes back to 1948. This is the annual freezing level over Ely, Nevada. And you can see it kind of bounced up and down here for the first 30, 40 years or so. And then starting about the mid-90s, the freezing level has come up about 500 or 600 feet. Last year was the highest freezing level in this record, and it was about 800 or 900 feet above the long-term mean. So this definitely is going to have ecological consequences in the mountains and hydrologic. If you break this up into the seasons, the picture isn't quite so simple. We don't really see, I've looked around a lot at this, I don't see a lot of evidence for very much warming taking place in the winter months. We see a little bit more in the spring on the upper right, and then the summer didn't do a lot for a long time until about the year 2000 or so. Summer has really popped up, and it's been quite warm since then, and then autumn hasn't done a lot, but lately it's been a little bit more on the warm side. So the seasons haven't all been the same. This is a picture of the White Mountain, or of the White Mountains right here, and looking back at Sierra Nevada. The city of Bishop, California is right in the middle, so we're looking west, again from another Southwest Airlines flight, on the way down here to Las Vegas. And it turns out that you can take the readings of the air temperature, the free air, the air just in the middle of nowhere, at about 600 millibars, and correlate those with a mountaintop station that we have right on the tippy top of White Mountain summits at 14,000 feet, and we've got hourly readings that we're making there. And you can use those to generate, to try to reconstruct what the climate is up there, and you can do it quite faithfully. There's a regression diagram here, and we can get most days within about 2 or 3 degrees C. Probably 95% of the days we can estimate it pretty accurately. So based on a short record, we can boldly go forth and reconstruct what the history of White Mountain Summit should be back to 1948, which is when this record starts. And you can see it's got this typical kind of thing that at the higher altitudes don't necessarily have to behave the same way as the lower altitudes. And it's kind of on the cool side over much of this record, and starting here about 1995 or so, it's come up. And the last year was the second in this record, and there's been a bunch of warm years at high altitudes. So, and this is the spatial pattern of the freezing level elevation, the trends in the freezing level elevation all over North America. The one interesting thing that I've noticed here in these diagrams is that there isn't much of a trend in the winter months, but there is a pretty good trend in spring, summer, and autumn. Believe me, the glaciers are taking notice of this. And I won't go over this one. So, this is so what about precipitation? This is 11 western states precipitation record. A couple of things on this diagram. There is not a decided overall trend, plus or minus. This is the water year precipitation ending in September for the 11 western states. And you can see it's got a lot of ups and downs. There's a maximum period here where they sorted out the Colorado River. And then there's been another kind of wet period here, especially in the southwest. It's come down since then. And then this is looking at October through March. So this is the winter part of the year. This is the really important part of the precipitation year for the west, because that's when our snow comes. That's what usually drives the hydrologic system for most of the rest of the year. We also have a decided change. Look at this little period right here, about 30 years or so. Not a lot of up and down. And then since then, we've had all kinds of up and down. So the variability has really increased over the last 30 years or so. And every one of these things that we're looking at with climate, some part of nature is paying close attention to. Nothing happens all by itself in this system. So one thing about some of the climate trends over North America and the precipitation, the West comes out kind of small in these diagrams. But in general, the eastern United States is getting wetter. The western United States, not quite so much. That's kind of the message that comes from these sets of diagrams here. And here's just the last few years. The winter before last was one of the wettest on record. So the purple areas are quite a bit above average, the red areas below average. So this is the water year 2 years ago. This is last year, which is just almost the total opposite of that. And here's this year so far, up through last Friday. And it's been another very dry year. And the temperature is kind of a mixed bag, some plus, some minus. Because we've had these dry conditions, we've had some pretty big fires. In fact, in the last 15 years, 7 of the 11 western states have had their biggest fire in their state's history. And 2 of those states, one of them is Oregon shown here, have had 2 fires that each broke the record, and the next one broke the old record that was just set. So there've been a lot of big fires lately. This fire right here is 558,000 acres. Really huge. It was in the middle of July. And it looked like some kind of moonscape or something that Curiosity is returning from Mars, these pictures. And if you look at the number of acres burned in the United States from 1960 onward, we've had a decided increase in the number of acres burned in fires. Last year was about 9.3 million acres. The average for the last 15 years or so is about 6, and that's higher than the long-term average. So we've had drought in the western states. This is the U.S. Drought Monitor for each year, near the end of the water year. This drought monitor started in 1999 as a result of a drought in a really, really important place called Washington, D.C. And it turns out there are droughts in other parts of the country too. And the western states have had droughts in their landscape every single year since this product started. The biggest one was in 2002, 2003, border to border, pretty severe drought. But if you go onward here, there's every year at the end of the water year, there's drought somewhere in the western United States. And here we are this year. And now we're looking at a not really great situation. We're still in March, and the prospects are not that great, actually. And we had the Midwestern drought, of course, which was huge in the news last year. So that's where we sit and expect a drought. So partly because of this, we put together a little tool, which is also on the web, called the West-Wide Drought Tracker. And this is in conjunction with the University of Idaho. And it's on our web pages. It uses the PRISM data. It's 4-kilometer gridded data. We have temperature, precipitation, Palmer indices, standardized precipitation index, standardized precipitation evapotranspiration index over periods of 1 to 12 months. It goes from 1895 through the current period. It consists of maps and time series, and I just happen to show what the year 1934 looked like. But you can go back and look at any year in a fair amount of detail back to 1895. And one of the other things you can get from this is time series. So this is a time series of the Palmer Drought Severity Index for the month of August, and we've taken all the pixels in the state of Idaho, all the pixels in the state of Nevada, and in the state of New Mexico, and shown what the Palmer Index is based on all of those back from 1895 up through August of last year. Just to give you an idea, it's especially interesting here down in New Mexico, that really wet period when we switched to having a lot more El Niños than we did in the prior 30 years or so. This really wet period down here engendered a lot of growth, trees and shrubs and so forth, and then it dried out, and now we have all the consequences we're seeing ecologically and with fire and so forth. So looking at the Colorado River system, this is a huge issue. I mean, it's just right out the back door here, and water on your tables is probably coming from there. About 85% of the flow of the Colorado River comes from about 15% of the area. The mountains are really important for the Colorado. And looking at what the climate might bring, the projections are, first of all, the precipitation does not have to go down for the stream flow to go down. All you have to do is raise the temperature. So raising the temperature, the estimates are, this is a decline of about 2 to 9% in the flow at Lee's Ferry, the important point between Glen Canyon and Lake Powell. A 1 degree rise in temperature is sort of equivalent to reducing the precipitation by the stream flow by 2 to 9%. So for a 3 degree rise by later in the century, we're looking at an estimate of maybe a 10 or 20% reduction in the flow of the already over-allocated Colorado River system. So a lot of you have seen this. This is the storage in Lake Powell. Right now it's 49% full. This goes back to 1963 when they started to fill it. Here's the elevation. Right now it's 100 feet below full. It's dropped 60 feet in the last 2 years. It's supposed to drop another probably 10, 15 feet this year. And this is Lake Mead, which is currently about 53% full. So you can look at it, I don't know which way to look at it, whether you're an optimist or a pessimist, but whether Lake Powell is half empty and Lake Mead is half full, or whether Lake Powell is half empty and Lake Mead is Lake Powell is half full and Lake Mead is half empty. So, but we're running about 50% for these the two biggest reservoirs in the United States. And we have the usual bathtub ring that we've seen here. And another thing is you'll see some of the forecasts this year. They're calling for like about 45% of runoff because we've had such a dry year into Lake Powell. They recently revised, just this year, the 30-year means that they're using. Those 30-year means have come down. So you're seeing this year's figures are referenced to a mean which has dropped from about 8 million acre feet to about 7 million. That's dropped about 11%. So if you see some percentage this year, last year that percentage would have been even lower because they've lowered the climatology. This is true in other parts of the West too. I've got an example from the Snake River where the climatology dropped by 9%. So all of the forecasting processes has made this adjustment just this year. So if it turns out that if we look back further, and the trees have a ringing message for us that This system can produce droughts that you guys haven't seen in your little lifetime here of 50 or 100 years in the 20th century. There are really long droughts that can and have occurred in the Colorado River system, much longer than what we've seen now. And the big question that's in front of us is the drought that we're seeing one of these that's induced by climate change, or is it one that's induced that just sort of comes naturally, or is it some combination? So I want to switch gears here now and switch to, we often talk about means and so forth, but I call these the climate we remember, which is the extremes of climate. So let's take the Las Vegas airport as an example. It sits right in the middle of town here. We got this brown area in the middle of a sort of a green area, artificially green, surrounded by a brown area. And there we have a temperature and a precipitation gauge. And so here's what the temperature shows at the Las Vegas airport, which the record starts around 1940. And it goes along until about the mid-70s and then starts to climb. But if you break this down a little bit more, you got two interesting things going on. For some reason, the temperature, mean annual maximum daytime temperature, dropped for about 30 years. And then it's been more or less constant for about the last 30, 35 years or so. If you look at the nighttime, it's a whole different story. Nighttime minimums have been rising. They've come up about 9 degrees Fahrenheit in that amount of time. There's a few breaks in there. So that's what the means have been doing. If you look at what I call the temperatures you remember, so these are the highest temperature of the year recorded in Las Vegas. So that runs typically around 113 degrees or so. This is the warmest day, plus or minus maybe 2 or 3 degrees, somewhere between 109 and 117. And you look at this, you see, am I seeing any kind of trend there? And I sort of chose stars deliberately here because these sort of look like constellations, okay? People look up at the stars and say, oh, it's a camel, or oh, it's Abraham Lincoln, or it's a car or something. So you can just sort of see for yourself whether you think this is changing or not, and try to put any other kind of guidance on here. This is the highest maximum. How about the coldest day of the year, the coldest daytime temperature of the year, which in Las Vegas runs typically 40, 45 degrees, somewhere in that range here. There's sort of a trend, or there's sort of a pattern that maybe the really cold days, they have had days here where it hasn't reached the freezing level back in the 60s. We haven't had a day that's in the last 20 years or so that looks like it's about maybe 36 degrees or so. So maybe the bottom has come up a little bit. The top doesn't seem to have gone up much. And this is current through right now. How about the low temperatures? The lowest temperature of the winter in Las Vegas, it's been down to 8 degrees. But you can see since in about the last 22 years or so, you have 120 here. But there's a big white area down here that's all filled in here. So because of the other graph I showed you, the minimums. Now, what's behind this, whether it's urban warming or whether it's an actual thing, I think it's a combination because we see the minimums going up outside of the cities. This is an urban airport, so it's not the greatest place to be looking at, but it's got a really good record. But we see the same thing in the urban locations. Something very similar, not the same thing, but it is getting warmer at night in other more podunk locations. And here's the high minimums. In other words, once a year expect a minimum around, back in the day, of maybe 85 degrees was a warm night here. Now 90 degrees is considered a warm night. So the nighttime minimums have been coming up, the extremes. And we have one there that's 96 degrees for the coldest part of the day. Let's switch to precipitation. We look at the Clausius-Clapeyron equation. The amount of water that the atmosphere can hold goes up dramatically as temperature increases. It goes up 35 or 40% for every 5 degrees C. Every 10 degrees C, a rule of thumb, is about doubles. A warmer atmosphere can hold a lot more water. So when we run these through a bunch of these climate models, and we just had a paper come out on the probable maximum precipitation, the climate models show that in the current climate, we can expect to see here in the tropics, this is the maximum, about 70, 75 millimeters of moisture in the air. If you squeezed it all out, you get maybe about 3 inches of moisture. If the climate warms up because of that equation I just showed, the amount it can go up, that the air can hold goes up quite a bit, and it's on the order of 30 to 50%, even 60 in some places. So what you might think is that a thunderstorm or a storm of some sort has more moisture available and it can rain more intensely. So just as I again chose Las Vegas Airport, went through the last, since 1937 in this case, what's the wettest day of the year? Calendar day in Las Vegas. Well, if you look at this, you can see, if anything, it's maybe on the way down a little bit. Last year actually had the second wettest day in the record. But it doesn't have to fall between midnight and midnight. It might fall some other time. So I picked 2 days. So here's the wettest 2 consecutive days of the year. And I'll just continue with this. Here's the wettest 3 consecutive days. Last 30, 40 years don't seem to show a heck of a lot of trend. Last 4 consecutive days, the wettest week of the year, 7 days. And then round out to 10 and 20 and 30 days. So when we go to these longer durations, we get away from that one gauge at the airport being so important, because it's sort of more of a regional signal when we get out further. And all of these durations matter for different engineering purposes. We spend tens and hundreds of billions of dollars on infrastructure based on these numbers. These are really important numbers. They have a lot to do with the way we build infrastructure in this country. And so the people who put these charts together about what the engineering standards should be followed have examined this issue. And in the areas in red here, they've looked at a lot more stations than just Las Vegas. They found that over the last 100 years or so, that the trends in one-day exceedance values, if anything, have either gone down or stayed about the same. And when they looked at a whole variety of durations and return intervals, and I won't go through them all, about the only one that's gone up is the one in the dots here, which is the 6-hour precipitation. In other words, a thunderstorm can rain out what's in the atmosphere. It takes some convergence to bring in new moisture to replace it. But at least here in the Southwest, it seems that, if anything, these amounts have stayed the same or gone down just slightly. Contrast this to the rest of the United States. This is a paper that Ken Kunkel and several of us put together a few years ago, comparing the last 30 years, taking the wettest days inside the last 30 years, compared with the 30 years prior to that, the wettest of those 30 years. So it's 2 30-year periods here, roughly, or 20-year periods, I guess. And it turns out that the amount of water in the air on the wet days has gotten bigger in most of the eastern United States. But in the western states, if anything, it stayed, I get the cursor here, it stayed about the same. And in the California and Nevada, it's even come down a little bit. I think we all expect that this is going to probably end up going up, but I'm just saying this is what the observations are showing. I want to make a quick point here about how much the Earth can change in just a few days. We get a very good reading of the Earth's temperature every single day, and it's updated about 2 or 3 days lag. And you can see just this year, the purple curve on the top, in a space of about 2 weeks, the whole Earth cooled off by about 0.5 degree C. What can do this? The only thing I can think of is clouds. So this really illustrates the importance of clouds, and the climate models have got to get all this complexity correct to make a projection about climate. Actually, it's not quite as hopeless as it might seem when you first look at it. So, how would climate change, if it occurred, how would it actually be played out? Well, in let's say a 50-year period, there's 18,000 days or 439,000 hours, 438. The fluctuations in climate are going to be experienced through weather. They're going to just take place minute by minute, hour by hour, day by day, over this whole time. That's how it's actually going to happen. It's not some abstract thing. It's a real thing. It takes place minute by minute. And this is the way the natural systems and the human systems are going to react to it. Just an example here, this is Elko. There's a year's worth of temperatures in Elko. You can go on our website and print these out. This is the last 2 years, all the ups and downs of the daily weather, the last 10 years, and the last 18,000 days. And basically what we're talking about with the change in the climate is taking this whole graph and just slightly tilting it up. So about one of these marks over here, that's 10 degrees right there, that this whole thing goes up by maybe 5, 6, 7 degrees Fahrenheit or so. So this sort of, excuse me, sort of puts it in context, I think. Again, with precipitation, same thing. Here's a year's worth of precipitation at Elko. Here's 2 years. Here's 10 years. And if you've been counting rapidly, you've counted, there's 3,500 precipitation events in Elko, down in the bottom there, of 1/100 of an inch or more. And this shows each and every precipitation event in the last 50 years. And so we're trying to say, what about this is changing? Are the amounts going up? Is the spacing, the frequency, the really high values? You try to look at this and say, is there any changes in the extremes? You can do a visual analysis, you can do a more careful numerical analysis. But this is what really the world is going to be reacting to, is this kind of sequence. So I wanted to make another point here about changes in climate. This is from Lake Tahoe, Tahoe City, where the Truckee River comes out of the lake, using the CMIT-3 models, the A2 scenario. And there's 3 types of behavior I'd like to point to on this graph. In the blue is the interannual variation, the ups and downs. And think back to the curve I showed of the actual temperature for the west, which has a lot of those ups and downs. You see spikes every now and then, there's positive spikes, there's negative spikes. Then you see here's several years that are kind of warm, they're followed by several years that have cooled off quite a bit. There's about 10 years here. I've run a 7-year smoother over this in red, and you can see that the course of true warming never runs smooth. And we get periods here where it'll rise. Here's a period here for about 10 years or 15, maybe even 20 years where it stays kind of flat. All of a sudden it rises, then it stays flat for about 20 years. So when you look around and you say, you know, it hasn't warmed up in the last 4 years or so. Actually, if you look at the climate models, which have the oceans in them, the ocean is responsible for some of this behavior. This is another example from, it has that same model, but it's got several other models too, and I've run the same smoother over it, all to show that this irregularity, it's not a smooth thing, that we expect deviations from a constant rise. In fact, if we get a constant rise, I'm really, really suspicious. It just doesn't look right. This is the way it really works. It's got all these ups and downs in it. And we're going to be seeing those. And if you imagine yourself as society perched and following this along, what are you going to be saying at each and every point on this graph? That, well, it hasn't been warming up lately, or it's really warmed up a lot lately in some of the rising periods. And every one of these models has climate change in it because they're all going up, but they get there by a whole variety of different trajectories, any one of which is possible. We just don't know. So I want to just say a little word about a little tool here that's been put together at the International Research Institute called the Timescales Exploratory Tool. And it tries to break up. So we're looking at the western states here, and it averages all the values this goes from Mexico to Canada. And we can break this up, a climate record for the West, into these 3 components. The red one here is the sort of long-term trend that's correlated with the global mean temperature. We have decadal scale variation, which takes 10 or 15, 20 years to go through cycles and deviations. That's in the green. And then we have the interannual variation, the rapid ups and downs, rapid being a year. And we can add all those together to get the full record. And it turns out the trend is only accounting for maybe in the West about 13% of the total. We still have decadal scale variation and interannual variation, and all of these have different reasons for existing, different sources, different things that are driving them. It's not always the same thing. So this whole issue is that climate variability remains a really big deal. The world isn't all global warming. Just as when we discovered El Nino, it turned out the world isn't all El Nino. But it's not unimportant. We have to deal with both ends of this. This is sort of the pre-existing condition. So I got 2 more slides here. I've just been reading this really interesting book called 1493 about what happened from the moment Columbus put his foot in the sand in 1492, what's happened all around the earth. And it just was a pretty stunning reminder of the amount of change that has taken place around the globe that's going on all the time. Change is nothing new to this system. It's just really astonishing. I'd really recommend this book. And there's another issue here. The change is already in the pipeline. The carbon dioxide we put in the air, we're not going to get back. It would be very, very difficult, if ever, to do that. And we're putting more in. Can't call it back, can't put the genie back in the lamp. So we have to deal with it. So I have some summary points here, and I've gone through most of them already. About the only ones I really want to emphasize here are climate change provides one more source of variability, but the old variability, so to speak, our pre-existing condition, still holds. We still have all that. The system still has unrealized warming because it doesn't respond immediately. It takes a while for the oceans to warm up. The Earth radiation is not in balance. Our checkbook still has more income than outgo, so we're going to warm up some more, even if we shut off all the emissions completely right now. And this leaves us with this very interesting choice between adaptation and mitigation, and I like the way it's been phrased here. It's the difference between managing the unavoidable and avoiding the unmanageable. And that's kind of where we're perched right now, and it might be some of the topic of this meeting here. So that's a picture of Great Basin National Park, Mather Climate Station at 9,100 feet. Thanks a lot. Appreciate it.
Yes, does anybody have any questions for Kelly? I was a lot of information. Please step up to the microphone and ask your questions so everyone can hear. Their microphones are right here.
Okay, I'll talk loud. Oh, there we go. Michael Nussbaum, I'm the education component lead, and I'm interested in the fact that the minimum temperatures, or the nighttime temperatures have been going up, but not the daytime temperatures. And I'm wondering how I would explain that, the reason for that to like high schoolers, or, because you would think about it, if the base is going up, the whole thing would go up. So, can you explain sort of the causal mechanism of why that is?
So I'm wondering the same thing. I honestly don't know the reason. And when we look at the climate models, they don't seem to have this behavior in them. They raise the max and the min more or less equally. So to me, this is kind of one of those unsolved mysteries, is why do the minimums, especially in the western states, I think it's more of a western thing than an eastern thing, why are the minimums going up? Minimums are more, what happens at night is the atmosphere gets decoupled from the upstairs. In the daytime, it all mixes pretty well. At night, because it's so dry in much of the west, it cools off pretty rapidly, and it cools off more at the surface. So the surface can do different things than up above. There's nothing unphysical about that. But why the minimums should be acting differently than the maximums, especially over kind of a dry state like this? We see it also in other parts of the west too. It's not just Nevada. California has the same thing, and what's been invoked there is maybe changes in the moisture. Water vapor is a very significant greenhouse gas. But honestly, I can't tell you.
Thanks.
We have time for one or two more questions. Keely? Yeah, please step up.
Hi, Kelly. Thanks for your talk. Keely Brooks with Southern Nevada Water Authority. I want to talk about extremes and precipitation. I just want to make sure that I got what you were saying in your presentation in terms of the observations that you looked at for Las Vegas and precipitation. So the precipitation record for Las Vegas is not showing a change in extremes, correct?
For Las Vegas itself.
Mm-hmm.
Or you could see what it was, I'll put it that way.
Right. I just want to make sure that that point is highlighted. And then, but yet, what are the projections saying?
I think most of us are still thinking that it is going to go up. It's hard to see why it wouldn't.
Right.
That's kind of the issue here. Now, why we can have differences from east to west because we have large-scale patterns in the atmosphere. The west is often different from the eastern United States, but I think the general thinking, I've had a lot of discussions with hydrologists and climatologists about this very issue of the West being a little bit different. It al- it also has to do with the way we think, the way the Pacific Ocean is warming up. The Pacific is warming more in the western side than the eastern side. And that asymmetry in the warming of the Pacific Ocean will be reflected in the giant patterns that take place in the atmosphere over North America. So it's possible, and that's the source of some of these decadal scale variations I was talking about, that what goes on in the ocean, I mean, we're in the driest part of the United States, but we're affected by the wettest part of the world. So there may be some ties here that are responsible for this, and it might be just a temporary thing. You know, these 5, 10, 15-year periods where it doesn't seem to be going along with the program, so to speak. Or it could be, since we're making predictions, there's always a dim possibility we could be wrong.
Thank you. And just one other comment about the urban heat island effect. You also pointed out, you also made a comment saying why you thought that what we were seeing with minimums and why maximums weren't changing, why you thought it wasn't just urban heat island. And that was that you are seeing the same pattern in the rural areas.
Yeah.
Correct?
And there's one other point about showing Las Vegas, because that's actually where people live. I mean, it might be partly artificial, but there's a few other artificial things around here I've noticed. And if that's part of your environment, that's part of your environment. I mean, it's we want one type of pristine kind of measurement to know what the system is doing, but we also want measurements from where people and plants and animals really are. And if they're there, and they are here in Las Vegas in droves, that also matters too. So what goes on in the urban areas matters.
Right, because we're going to have to adapt to climate change and urban heat island, and so either way, we got to be prepared for these warmer temperatures.
So our trick is to know what's going on generally, and then what are the local deviations from that, and what is behind those deviations. We need to understand both sides of this, because if you want to get down to where people and plants and animals really are, you know, it's very localized to us and our structure of civilization.
Thank you very much.
Okay, Kelly, thank you once again for an excellent introduction to our topic here, and hopefully this will help frame our conversations later today. And we're now scheduled for a break, so as Tom started with his little 2-minute intro, I challenge each of you to try to meet, and let's say at least, let's make it 3 so we can have at least 5-minute conversations. 3 new people, find out what they're doing, and Kelly will be around and available to answer any other questions. His presentation will be on the internet. And so we now have a break until 10:15, and we will start at 10:15 sharp with Pat Mulroy talking about what Southern Nevada Water Authority is facing under climate change scenarios and providing water for this big population center here